Good morning. Okay, today I'm going to explain line coding techniques. Line coding techniques. Okay, before going to explain this line coding technique, we know the block diagram of digital communication. The block diagram of digital communication consisting of information source, source encoder, channel encoder, digital modulator, transmission medium, digital modulator with the carrier signal, transmission medium, digital demodulator with the carrier signal, and channel decoder, source decoder, and destination. Now I am not going to explain this entire parts of digital communication. We are already discussed in the classroom, right? Now I want to ask one question here. What is the input of digital communication and what is the output of digital modulator? What is the input of digital modulator and what is the output of digital modulator, right? We know that if you go through analog modulators and digital modulators, in analog modulators, input, that is a message signal or whatever the signal, that signal is always in continuous time. In digital modulator, the input signal is in the binary format zeros and ones. In carrier signal in analog modulator is continuous time. Digital modulator is also in continuous time. Modulated signal S of t in analog modulator continuous in time. In digital modulator is also continuous in time. The main difference is that the input is in analog modulator is a continuous time signal and digital modulators is in the form of binary format. Right? Now we know that any continuous time signal is converted into a digital. The steps are sampler, quantizer, then encoder. Output of encoder is zeros and ones. So to convert any continuous time signal, this is the format to convert a digital signal. So what is this zeros and ones bits represented? It conveys the information of analog. Now I want to transmit this data, this zeros and ones, through any medium. Why it is called as a line? So I want to transmit this binary data through a line or a medium. So if you want to transmit this data directly through a medium, it is not possible. So I cannot transmit this data, this zeros and ones, through a transmission medium. So what I have to do? First I want to convert this zeros and ones into a waveform. The basic operation of line coding technique is used to convert a bits to waveform. The line coding technique, it is used to convert a binary bits to a waveform. Okay. Now some books, this conversion is also called as a baseband modulation, right? The ultimate aim is we are only two levels, that is zeros and ones, only these two levels, zeros and ones. These zeros and ones we are representing in the form of waveform, right? Now we will see now what are the different possible way we can map this zeros and ones. Now the basic pulse shaping techniques, the basic pulse shaping techniques are basic pulse shaping techniques. The basic pulse shaping techniques are, there are three types of pulse shaping techniques. One is unipolar, second one is polar, third one is bipolar. First, if you see the unipolar technique, unipolar technique, pulse shaping technique, right? Now, in unipolar technique, the bits are zeros and ones. These bits will be represented in a levels, that is in the voltage V. Now, there are only two levels V available. The bit 1 is represented, a level is plus a volts. Okay. Bit 0 is represent a level with 0 voltage. Similarly, second method is polar. In polar method also, bits and levels. Here also bit 1 will be represented plus a levels, lay voltage, bit 0 is represented minus a volts. Similarly, in bipolar format, third one, bipolar, here also bits and levels. In bipolar also, bit 1 will be represented either plus A or minus A, and bit 0 will be represented level 0. Okay. If you observe in bipolar format, pulse shaping technique, bit 1 will be represented plus A minus A, as well as bit 0 will be represented 0 voltage level. So here we find 3 voltage levels, plus A, minus A, as well as 0 voltage levels. Because of it consisting of 3 voltage levels, this method is called as pseudo ternary code. This method is also called as pseudo ternary code. Pseudo ternary code. Okay, what is meaning of ternary? 3 voltage levels. Okay, and another one, for example, if I got 3 voltage levels, 3 1 bits, so each 1 bit will be represented either plus A or minus A. For example, so for this duration bit is 1, second duration bit is another 1, third duration bit is another 1. Okay. Now if you see here, the first duration 1 will be represented plus A. Next, okay, alternative another 1 is represented minus A, another 1 is represented plus A, right? So here the bit 1 is marked as a alternative plus A as well as minus A. So this method is also called as alternative mark inversion method. Mark inversion method or codes. This is also called as AMI codes. Okay. Now these three are the pulse shaping techniques. One is unipolar. In unipolar, bit 1 will be represented plus A volts and bit 0 will be represented 0 volts. In polar, polar means it consisting of 2 voltage levels. Bit 1 will be represented plus A volts, bit 0 will be represented minus A volts. Bipolar, in bipolar, bit 1 will be represented plus A or minus A. Here we can call it as either plus A minus A, bit 0 will be represented 0 volts. right? So because of three voltage levels, this method also called as a pseudo ternary code. And if you find in the data alternative ones, so this method is also called as a alternative mark inversion codes. Okay, now so these are the pulse shaping techniques. Now we will learn what are the pulses will be available. Okay, now we can see here what are the pulses, available pulses. So here basic available pulses, basic available pulses, right? The first pulse name is non return to zero. NRZ, non return to zero, right? This non return to zero pulse, see here, this is my x axis time period, y axis amplitude levels, we can call it as. Now for example, this is the TB duration. Within TB duration, the pulse is not returned to zero level. Within TB duration, the pulse is not returned to TB duration, TB level. So that is called, it is called as a non-return to zero pulses. So within TB duration, the pulse is not returned to zero. So here the pulse, it occupies entire TB duration. This pulse occupies entire TB duration. TB is here bit duration. Bit duration, right? Now this is non-return to zero. This is a voltage level, this is a TB duration. Now next pulse we can see here, next pulse name is return to zero. That is RZ, return to zero. Return to zero pulse. So in return to zero pulse, this is my TB duration. Now remember here, within TB duration, the pulse will be returned to zero level. Within TB duration, the pulse is returned to zero duration. Where the pulse is returned to TB zero level is, that is exactly at TB by 2. The pulse will be returned to zero exactly at TB by 2. So here the pulse will occupies half of the bit duration, half of the bit duration. Half of the bit duration, right? Next one, this is the second one. Third one, Manchester pulse. Manchester pulse. Third one is Manchester pulse. So in this case, TB duration. Okay, in this Manchester pulse, it consisting of two voltage levels. At TB by, this is half duration is called TB by 2. The first half bit duration, it will be high. The first half bit duration will be high, and the next half bit duration will be low. Okay, the first half bit duration will be high, the next half bit duration will be low. Okay, this type of pulse is called as a Manchester pulse. Now we saw that the basic pulse shaping techniques are, okay, unipolar, polar, bipolar, and available pulses are NRZ pulse, return to zero pulse, Manchester pulse, right? Okay, now we can solve some examples so that it is easy to understand for you. Let us take one example. A binary sequence BL 1 1 1 1 0 0 1 comma 0 represent this binary sequence into unipolar NRZ. Represent this binary sequence into a waveform format by using unipolar NRZ. Right? So, to solve this problem, first I want to explain step by step. The first step is step 1. Step 1. First step is here we have to convert a bits to level mapping. Bits to level mapping. Okay. Bits to level mapping. First step is bits to level mapping. Right. Bits to level mapping. First step. The bits to level mapping is first what technique we are using? Unipolar technique, right? Unipolar NRZ technique we are using. So that here I want to write unipolar technique. In unipolar technique, bit 1 is mapped to plus A volts and bit 0 is mapped to 0 volts. Okay, for example, we can consider plus A volts or A volts is equal to 2 volts. For simplicity to understand, A is equal to 2 volts. So here bit 1 is mapped to A volts and bit 0 is mapped to 0 volts. First, bit to level mapping. So the given sequence, after level mapping sequence, I am representing that BL with capital BL. 1 will be represented with what? Plus A volts, right? Plus A volts. Plus A volts means A value is equal to what? 2. 2, 2, 2, 2. Bit 0 will be represented with what? 0 voltage. Again 2 volts, again 0 voltage. Right? Now this is the first step. Second step. By using this voltage level, I am going to draw the graph. Now this is my time axis T. How many levels? 1, 2, 3, 4, 5, 6, 7, 8. 8 deviation, first duration, second one, third, fourth duration, right? So these are my duration levels. First duration level, here voltage level 2 volts and this is 0 volts. First duration level, here voltage level is 2. Second 2, third 2, fourth 2, up to fourth duration, the voltage levels are 2 volts. Now here duration level 5 and 6, voltage level is 0. Then again 2, then 0. Okay. So here this is NRZ means non-return to 0. Non-return to 0 means within TB duration the signal is non-return to 0. Next to TB duration the signal is non-return to 0. This is a unipolar. First by using unipolar technique, first I made bits to level mapping. Next by using available pulses, right, I am drawing this graph. Okay, I hope all of you clear for this example. Okay, first we are completed. Second one we will see here, second example. Okay, polar NRZ. The same problem I want to represent by using polar NRZ. So the given bit sequence is equal to, yes, 4 ones, 2 zeros and 1 and 0. Now I want to represent this bit sequence in the form of waveform using polar energized. The pulse shaping technique is polar, available pulse is energized. Okay. Now, what is the first step? What is the step? Okay. Level mapping step. Level mapping step. What is the level mapping in polar? Bit 1 will be represented with plus A volts, bit 0 will be represented with minus A volts. In polar we are finding two voltage levels, that is plus A minus A. We know that A is equal to 2 volts. Now the capital BL is equal to level mapping. 1 will be represented with what? Plus A, that is equal to 2 volts. Right. Next again 1 means 4 ones means 4 2 volts. Next 0 voltage will be represented with minus A volts means minus 2 volts. Minus 2 volts, plus 2 volts and minus 2 volts. Okay, right. Now I want to draw the graph. This is T. Okay, TB, 2 TB, 3 TB, 4 TB, 5 TB, 6 TB, 7 TB and 8 TB. So here the available pulse technique is energized. Within TB duration, the pulse is not returned to 0. So for first TB, second TB, third TB, fourth TB, up to 4 TB periods, the voltage level is plus 2 volts. Right. Next, from here to here, next 4 to 5 TB and 5 to 6 TB, voltage levels are minus 2 volts. Then again voltage level is plus 2 volts, again minus 2 volts. Right. Okay. This is polar energized. Okay. Now third example is bipolar energized. Bipolar energized. Right. So in bipolar energized, what is the first step? This is the step 1 here, this is step 1, this is step 2. Now similarly here also step 1. What is the step 1 here? Level mapping, yes or no? Level mapping. Level mapping in bipolar, the bipolar technique. Bit 1 will be mapped to either plus A or minus A. Bit 0 will be mapped 0 voltage. Right. Here A is equal to 2 volts. Minus A is equal to minus 2 volts. Right. Please remember that. Okay. Now this is a level mapping. So here BL is equal to, after mapping the level, first bit 1, yes, first bit 1 is represented with plus A, that is 2 volts. Second bit, alternative bit, second bit is 1, means that is represented minus 2 volts. Similarly plus 2 volts and minus 2 volts. Then 0 will be represented 0 volts. Again minus 2 is completed, again plus 2 volts, 0 voltage. This is the first step, that is level mapping in bipolar energized. Right. Now step 2 is, here we have to draw the graph. Yes, TB, 2 TB, 3 TB, 4 TB, 5 TB, 6 TB, 7 TB, 8 TB. Right. Voltage levels plus 2 volts and minus 2 volts. Now tell me, first TB duration, what type of available pulses? Energized pulses. So first TB duration, the first TB duration is plus 2 volts. Next TB duration is represented with what? Minus 2 volts, plus 2 volts, minus 2 volts. Now After this fifth duration is represented with what? 0 level. Sixth duration also 0 level. Yes, minus 2 volts is completed, again positive level. Right? This is the second technique, that is a polar NRZ. Now if you see here, by using three pulse shaping techniques, unipolar, polar and bipolar, I represented all using NRZ pulses, all the cases. Now similarly I want to represent using pulse shaping, available pulses is RZ. Okay. Next step is okay. Next one is same. Okay. Next one is unipolar RZ. Same example, that is BL is equal to 1 1 1 1 0 0. Okay, 1 0. This is my data or my input signal. Now I am representing this sequence of binary bits to waveform by using unipolar RZ. Right? So in unipolar RZ, the step 1 level mapping, bit 1 will be represented plus A volts, bit 0 will be representing 0 volts, and available pulse is RZ. Step 2, here A volts is 2 volts, right? This is T. Okay, TB, 2 TB, 3 TB, 4 TB, 5 TB, 6 TB, 7 TB. Now RZ, return to 0 pulse. Return to 0 pulse means within TB duration the pulse is returned to 0. So where the pulse will be returned to 0? At exact TB by 2 duration. Now see here, first bit is 1. So after level mapping, what is the BL here? BL is 2 2 2 2 0 0 2 0, right? After level mapping, first the bit is 2 volts plus 2 volts. Okay, now within TB by 2 duration the bit is returned to 0. Then again within TB by 2 duration the bit is returned to 0. Within TB by 2 duration the bit is returned to 0. Within TB by 2 duration the bit is returned to 0. After this fifth and sixth duration the voltage level is 0 again and again 0. Okay, this is unipolar RZ. Okay, next one, polar RZ. Polar RZ. Polar RZ. So in polar RZ, step 1 level mapping, bit 1 will be represented plus A volts, bit 0 will be represented minus A volts. Okay, after level mapping 2 minus 2, sorry, 2 plus 2, 2 2, here 2 zeros means 2 minus 2s, and 2 and 0 means minus 2. Next, now next step, to represent this one into waveform T. See here, some books represented here TB, 2 TB, 3 TB, 4 TB, 5 TB durations, or some books also be represented here normalizing time period TB. This is by writing T by TB we can give here 1 2 3 4 5 6 7 8. Okay, this is also possible to represent this waveform. Okay, here by writing the normalizing time axis, that is t by tb, or by representing tb 2tb 3tb, both are same. Okay, now here what are the voltage levels? Two voltage levels, that is plus 2 volts minus 2 volts. So this is a plus 2 volts minus 2 volts. What type of pulse available? Return to 0, means within tb duration the pulse is returned to 0. The first level is 2. The first level is 2 volts. Second level is also 2 volts. Third level is also 2 volts. Fourth level is also 2 volts. Next, this fifth level is minus 2 volts. Sixth level minus 2 volts. Next, plus 2 volts, minus 2 volts. Right? This is polar RZ. Now third one, bipolar RZ. Third one, bipolar RZ. Bipolar RZ. Here the pulse shaping technique is bipolar. Available pulse is RZ. Right? The step 1. Step 1 is level mapping. Level mapping. So what are the levels here? Level mapping. S plus, 1 will be represented plus A minus A. 0 will be represented 0 volts, right? So 3 voltage levels, plus A minus A, 0 volts, that is plus 2 volts, minus 2 volts and 0 voltage, right? So BL is equal to plus 2 volts, minus 2, plus 2, minus 2, 0, 0, minus 2 is completed, then plus 2, 0 volt. This is a level mapping. Right, the waveform now here. Step 2, T by TB. 1, 2, 3, 4, 5, 6, 7, 8. Right? Now, see here. Voltage levels, plus 2 volts, 0 voltage, minus 3 voltage levels. Available pulse is return to 0 within the TB duration, that is return to 0. So first plus 2, next one minus 2, plus 2, minus 2, plus 2. So after first, second, third, fourth completed, after fifth duration is a zeros. Yes, 0, 0, then again plus 2, 0. Right? This is polar RZ code. The only one left, that is Manchester coding. So here I want to represent Manchester. So polar Manchester, if you see, we will see the polar Manchester. Polar Manchester. Example, BL is equal to what? Right? Here the pulse shaping technique is polar. Available pulse is Manchester. Okay. First, step 1, level mapping. So I want to directly map here. Level here, polar bit 1 will be represented plus A volts, bit 0 will be represented minus A volts. Voltage level is 2 volts here, minus 2 volts. So that BL is equal to 2, 2, 2, 2, minus 2, minus 2, 2 and minus 2. Next, waveform T by TB. 1, 2, 3, 4, 5, 6, 7, 8. So in Manchester pulse also it will be first half of the duration. In Manchester pulse we know that this is a TB period. First half of the duration will be positive level, next half of the duration will be negative level. Yes or no? Now see here, first bit is a 2 volts. First half of the duration here, voltage level 2 minus 2. First half of the duration will be positive, next half of will be negative. Similarly, next see here 4 TB duration is completed, fifth TB duration again minus 2, so it will be continuous up to TB duration, TB by 2. Then after sixth it is a positive value, it is continuous. Next here seventh duration, this is also continuous. Okay, this is polar Manchester, right? Okay, I hope you will understand all the techniques. Now I am giving one example. Please solve this question. The binary sequence binary sequence binary sequence BL is equal to this is my binary sequence. Represent this binary sequence into waveform format. First one, unipolar RZ. Second one, bipolar RZ. Third one, polar NRZ. Fourth one, bipolar polar Manchester. Fifth one, unipolar RZ. Okay, this is today your assignment. Okay, 21/04/2020. Thank you.